Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam there is uniformly varying load. It varies from 0 in the point A to W in the point B. The span of the beam is given as L. Analysis of this beam is a little difficult. To make the analysis easier, let us add UVL downwards in this way. We have added this UVL downwards, so same UVL should be added upwards. So there will be no change in the final answers. This portion can be taken as the uniformly distributed load. We know that the upward deflection due to RB will be equal to the downward deflection due to UVL. To find the upward deflection due to RB, this is the formula, and to find the downward deflection due to UVL, this is the formula. This is for the uniformly distributed load part, and this is for this uniformly varying load. We know that in this beam EI is constant, so we can eliminate EI so that we will get this equation. Now from the point B about the point A, we are going to find the bending moment values and then draw the diagrams. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. First, let us consider RB. It is acting in the anti-clockwise direction, so that it will be positive, and the distance is L. RB into L, we will get RBL. Now let us take the uniformly distributed load. It is acting in the clockwise direction, so that it will be negative. We know that with the load we have to multiply the distance and then the distance by 2, so that we will get WL square upon 2, and the diagram will be in the shape of parabola. Now let us take this uniformly varying load. It is acting in the anti-clockwise direction, so that it will be positive. In the case of UVL, we have to multiply the area with the centroid distance. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is W. So the area is half into L into W. We have to find the centroid distance about the point A. For this triangle, the centroid distance towards the point A is 1 upon 3 into breadth. Here the breadth is L, so 1 upon 3 into L. So the moment due to UVL is WL square upon 6, and the diagram will be a third degree parabola. Now let us find area 1 x1 bar. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is RBL. So this is the area. Let us find x1 bar. We have to find the centroid distance about the right side. For this triangle, the centroid distance towards the right is 2 upon 3 into B. Here the breadth is L, so 2 upon 3 into L. We can eliminate this 2 and this 2. L into L into L, it will be L cube. So for area 1 x1 bar, we will get RB L cube upon 3. Now let us find area 2 x2 bar. It is a second degree parabola. The area formula is 1 upon 3 BH. Here the breadth is L and the height is WL square upon 2. So this is the area, and the centroid distance towards the right is 3 upon 4 into breadth. Here the breadth is L, so it is 3 upon 4 into L. We can eliminate this 3 and this 3. 2 into 4, it will be 8. L into L square into L, it will be L power 4. So for area 2 x bar 2, we will get WL power 4 upon 8. Now let us find area 3 x bar 3. It is a third degree parabola. The area formula for the third degree parabola is 1 upon 4 into BH. Here the breadth is L and the height is WL square upon 6. So this is the area, and the centroid distance towards the right is 4 upon 5 into B. So 4 upon 5 into L. We can eliminate this 4 and this 4. 6 into 5, it will be 30. L into L square into L, it will be L power 4. For area 3 x bar 3, we will get WL power 4 upon 30. Now let us subtract area 3 x bar 3 by area 2 x bar 2. When we do that, we will get 11 WL power 4 upon 120. We have found both of these. Let us apply them. Let us take L cube upon 3 on the other side. It will come inversely. Let us eliminate L cube, and here it will be L. Let us eliminate 3, and here it will be 40. Finally, for RB, we will get 11 WL upon 40. Now let us apply the rule sigma V is equal to 0 and find RA and RB are acting upwards, so both of them will be positive. The UVL is acting downwards, so it will be negative. For the UVL, the total load is the area. We know the area of a triangle half into BH. Here the breadth is L and the height is W. So this is the area. In this way, we can find RA, which is 9WL upon 40. Now let us take a moment about A and find MA. RB is acting in the anticlockwise direction, so that it will be positive, and the distance is L. The UVL is acting in the clockwise direction, so that it will be negative. We have to multiply the area with the centroid distance. This is the area. For this triangle, the centroid distance about the point A is 2 upon 3 into B. Here the breadth is L. So 2 upon 3 into L. MA will be acting in the anticlockwise direction, so that it will be positive. Finally, for MA, we will get 7 WL square upon 120. By using the right hand side rule, we can find the shear force values in the point A, and by using left hand side rule, we can find the shear force values in the point B. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment in the beam. In this point, let us make a section and find the distance. In that point, I have made a section at a distance of x from the point A. We have to find this height. For the distance of L, the height is W. So for L, it is W. But I need the height at the distance of x. So we have to multiply with the x. In this way, we will get this height as Wx upon L. Now in this section, let us find the shear force, and we know that it is 0. RA is acting upwards, so that it will be positive. The UVL is acting downwards, so it will be negative. For the UVL, shear force is the area. This is the area of this triangle. We can take this term on the other side. It will come as positive. We can eliminate W. X into x, it will be x square. We can eliminate 2. Here it will be 20. We can take this L on the other side. L into L, it will be L square. Then we can take root on both of the sides, so that we will get x as 3L upon root 20. Now we know the value of x. Let us apply that. In the height formula, instead of x, we can apply 3L upon root 20. We can eliminate this L and this L, so that we will get the height as 3W upon root 20. Now let us find the maximum positive bending moment. We are going to find that from the point A. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. MA is acting in the anti-clockwise direction so that it will be negative. RA is acting in the clockwise direction so that it will be positive, and the distance is 3L upon root 20. The UVL is acting in the anti-clockwise direction so that it will be negative. For the UVL, we have to multiply the area with the centroid distance. This is the area of the triangle. The centroid distance towards the right is 1 upon 3 into breadth. Here the breadth is 3L upon root 20. So this is the centroid distance. After simplifying, we will get this. We can keep the expression of the maximum positive bending moment approximately equal to WL square upon 23.6464. We know that the bending moment in the point B is equal to 0. Let us find the bending moment at A. In the point A, we have MA, which is acting in the anticlockwise direction, so that it will be negative. Here you can see the bending moment diagram. In this point, the bending moment becomes 0. This is the point of contraflexure. We can make a section in this point and find the distance. You can see that I have made a section in that point at a distance of x from the point A. We have to find this height. For the distance of L, the height is W. So for L, it is W. But we need the height at the distance of x. So we have to multiply with the x. In this way, we are getting the height as Wx upon L. We have seen this before. Now in this section, let us find the moment. We know that it is 0. Using that concept, let us find the distance x. Using right hand side rule, we can find the moment. We have seen this already. From this term, we can take W by 2 outside and take it on the other side. 0 into 2 by W, we will get 0. We can take these two terms on the other side. They will come with a change of signs. Then for these two terms, we can take LCM. Then we can eliminate 60. Let us take L on the other side. L into L square, it will be L cube. Let us take this term on the other side. It will come as positive. Let us keep x is equal to KL. Then we can take L cube outside and take it on the other side. 0 upon L cube, we will get a 0. Then using a calculator, we can solve this equation. So that for k, we will get root 3 upon 5 minus 1 upon 2. We know that x is KL. Finally, for x, we will get this expression. Now we are going to make the expressions for the slope and deflection. We have to make a section in this beam. I have made a section randomly here at a distance of x from the point A. In this section, we have to find the moment. We know how to do that. Now let us equate the moment with the EI d square y upon dx square. Now using this formula, we can integrate this equation. In this term, there is no x, so we have to multiply with the x. When we integrate x, it will be x square upon 2. When we integrate x cube, it will be x power 4 upon 4. C1 is the constant. 40 into 2, it will be 80. 6L into 4, it will be 24L. Now let us integrate this equation. When we integrate x, it will be x square upon 2. When we integrate x square, it will be x cube upon 3. When we integrate x power 4, it will be x power 5 upon 5. When we integrate c1, it will be c1x. c2 is the new constant. 120 into 2, it will be 240. 80 into 3, it will be 240. 24L into 5, it will be 120L. We know that in the point A, there is a fixed support. In the fixed support, there will be no slope and no deflection. So when x is equal to 0, dy upon dx will be 0. Let us apply both of them in this equation so that we will get c1 as 0. And we know that when x is 0, the deflection y will be 0. In this equation, let us apply both of them. In this way, we will get c2 which is equal to 0. In the slope and deflection equations, let us apply the values of c1 and c2 so that we will get these two equations. Let us keep the slope equation as number 1 and let us keep the deflection equation as number 2. Now let us find the slope in the propped end. To find that in the slope equation, instead of x, we have to apply L. In this way, we will get the slope in the point B, that is theta B, which is equal to WL cube upon 80 EI. Now let us find the slope in the center. For that, instead of x, we have to apply L by 2. In this way, we will get the slope in the point C. Now let us make the expression for the deflection in the center. For that, in the deflection equation, instead of x, we have to apply L upon 2. In this way, we can find the deflection in the center. The deflection will be negative. That means it is downwards. Now we are going to find the location of maximum deflection. We know that there will be maximum deflection when the slope is 0. Let us take the slope equation and equate that to 0. After simplifying, we will get this. Let us keep x is equal to KL. We can take L cube on the other side. 0 upon L cube, it will become 0. Then we can take a calculator and solve this equation. For k, we will get this. And we know that x is KL. So for x, we will get this expression. Now in the deflection equation, instead of x, we can apply this so that we will get the maximum deflection approximately equal to WL power 4 upon 328.07 EI. Now we are going to end this session. Thank you for watching this video.